I'll give a presentation on hydraulic modeling and OpenMI. The previous days we have been using meteorological models and hydrologic models. The next step is then to go and model the hydrology of the river and eventually compute the flooding and compute what the impact is of the floods on the people and the environment. So that's where we are moving now, but hydraulic models aren't in the DRIHM platform yet, so that's why it's the last bit, and we show what will be the next step to include and what possibilities there might be in the hydraulic domain. So I will give a brief introduction on hydraulic modeling and some background on OpenMI, and then Quillon will go further into the OpenMI practical session. So we make the transition from hydrology to hydraulics. That's basically shifting our attention from the whole catchment, all the heterogeneity and land use, soil types. We move to the focus on the channels, the water flowing in the river system itself. So that's a change in scales, change in disciplines. Within the hydrology, you can also compute the discharge. What's the difference between hydraulics and hydrology? And in essence, it boils down to this element. Both hydrology and hydraulics need to take care of the mass balance. You don't want to produce more discharge than you had rainfall, or you don't want to lose water under the way. So that's the same in hydraulics. So continuity equation is basically the mass balance of the water. Both hydrology and hydraulics has it. But then in hydrology, you assume that the discharge is a function of the water volume in a grid cell, whereas in hydraulics, you start computing the momentum equations, where you have additional equations to solve for the U and the V component, the X and Y component of the velocity. So when changing from between these disciplines, what changes? Well, basically, you need quite different data sets. In this case, we focus on the rivers and creeks. We need some geometry for the rivers itself. So rather than using a large-scale DEM, digital elevation model, we need to focus on, well, what's the geometry of the river and the banks and possibly the floodplains. So for that, you can either use cross-sectional information, or if the river is a bit bigger, then you can use multi-beam sonar to get high-resolution information, although the shallow parts always remain a little bit of an issue of where do you get good data for that. You also need information on the dimensions and operational data for hydraulic structures. Are there any weirs, culverts, gates, barriers, dams? What else within the reach of interest? Also locations of and dimensions of bridges, which may constrict the flow area and cause flooding stream or flow resistance. And especially for floodplains, you need to know what's the vegetation characteristics, how easy can water flow into the floodplain. Is it a bare, simple grassland, or is there a dense forest or dense bushes blocking the flow? And in the main channel, you can see flow resistance, derive that from alluvial characteristics of a river, what type of sediment is there, so what type of bed forms will it, dunes or ripples will be formed during graph, and so sometimes sediment information is also relevant for your hydraulic simulation. So in short, you need much higher resolution data than for the hydrology and meteorology we've seen so far. So we go back to partial differential equations, almost the same equations that we started with in meteorology. For simplicity, we are focusing here on 2D hydraulics only, but if you generalize to 3D, then the equations become more similar to meteorology. An important difference is that water can be, in general, considered incompressible. So that introduces some additional features which are not present in meteorology. So let me go to these equations step by step. Well, we have the continuity, the mass conservation equation. The water level goes up if the flows, the discharges, water depth times velocity. If they are not equal, then the water level goes up. That's simple enough. If we then look at the momentum equations, we have acceleration, flow acceleration terms in two directions. We have momentum transport from upstream, so water starts flowing in a certain location faster if the velocity, if there is the water that flows into the grid cell has a higher speed, so that's flow from upstream, and you have flow from sideways. So if water, if there is a lateral movement in water, you can also have these acceleration terms due to that. In general, you can include also Coriolis forces, but usually it can ignore it in rivers. But if you have bigger open water bodies, there might be some influence. Then we have a bed level, basically bed slope effects and water slope effects are included in this term. You also include freshwater, saltwater transitions in estuaries in this term. Then we have a quite big term, the effective eddy viscosity due to all kinds of subgrid fluctuations, turbulence, fine-grained eddies which are not resolved by the grid tend to end up in this part. And then we have sources and sinks for momentum. Well, there should also be a source or sink for water, like rainfall and groundwater infiltration over here in the mass balance, but you have a similar term over here for momentum, like friction and resistance is included in that one. Well, for all terms here from acceleration until the pressure term, basically there are no calibration parameters, so they are known and given. So the biggest calibration parameters are the viscosity and the bed friction. Besides making sure that you know your geometry. And even for the viscosity and the bed friction, there are usually or formulations by which you can estimate what they should be. So with these 2D hydraulic models, it's very quickly that if you have the right geometry, if you have all the right information, your simulation will give the right answer. That's a big difference compared to hydrology, because there is all kinds of heterogeneity, and there is a lot more calibration and expert judgment in there. But if you change to 1D, and we'll do that in a minute, then some of the terms start to disappear. You lose a lot of these terms, and you lose some of the pressure terms because you ignore lateral variation in the water levels. And you lose basically the most part of the viscosity, so then more of engineering, expert judgment starts creeping in, and calibration becomes more important. So this is what we get if we reduce to 1D. Basically water level changes if the discharge in longitudinal direction changes. And we have the velocity, one velocity component in the momentum equations. However, this assumes that there is one water depth, but you will have, in general, a cross-sectional area with water depths varying across the width. So usually the first equation is written slightly differently, with A being the cross-sectional flow area and B being the width of the channel. So it's a more integral variant of the previous equation. So the picture is a well-known picture from the Hagers manual. Hagers is a public domain model developed by the US Army Corps of Engineers. And if you look worldwide, it's probably the most widely used one-dimensional hydraulic model. There are several other hydraulic models. We'll touch on the Masquerade system later, and that's the one we are aiming to include in the DRIHM platform. It's an open source model, so that makes it more attractive. Most of the other models are closed source still, so but yeah, it does not matter too much which hydraulic model you are using. Most of the characteristics are the same, but there are differences in the numerics. So sometimes if you have a steep river, you may have simulations crashing in one model and another model running because the supercritical flow is not handled well by all the numerical schemes around. So you usually can choose between an efficient, accurate scheme for subcritical flow or a more robust scheme that is also handling supercritical and transcritical flows. And I think the Hagers model is purely a 1D model, so if you have one river, one channel, you can do it, but if you have a network of channels, tributaries, you cannot include it in the model. They may have changed that a little bit, because I saw some very recent changes also towards 2D modeling, but that's the main limitation. So what are issues with 1D models? The model is quite simple and runs quite quickly, so it's ideal for ensembles and operational predictions. If you have very little time to run the model and you want to include also uncertainty, then 1D models are by far the best way to go forward. All kinds of elements like flow contractions and expansions, they don't give a one-dimensional flow pattern in a river, so the model does not represent accurately all the physics phenomena that occur in the real river. That's the same for the water level in bend. You go around the bend, the water level near the surface will not feel the bed, and it will try to go straight, and it can only be forced to go around the bend if there is lateral slope in the water level. So you have all kinds of these effects which may cause flooding more easily to occur in the outer band than the inner band. And so in the 1D model, you don't have these features. So there are good reasons to go to a 2D model, maybe the last one to say, okay, if I have a meandering channel, then during low flow, the flow path is around the bend, but during high flow, I basically follow the inner band. I flow over the floodplain, and that's the shorter path, and 1D models are not able to handle that well in general. You can tweak and use your knowledge of the new details to make it the predictions a bit better, but in general it's something to be aware of. So I'll switch now to the hydraulic model. We've seen the equation, so no reason to go there. And the question is, okay, what do we mean by a 2D hydraulic model? You can start with a Cartesian grid, just like meteorology and do. But then, okay, this is a river. Let's show some of the details. There are of hydraulic structures, weirs, and things like that, which are actually not visible on this scale, but they are all influencing the flow pattern. So if we then come with a Cartesian mesh, you cannot really resolve the details of the hydraulics unless you go and take a very high resolution Cartesian mesh with a lot of computational time. So in general, it's not really a good idea to use a Cartesian mesh for hydraulic modeling of rivers. So we come up with a different way of modeling. We take the same river and then we cover that with a curvilinear mesh. To zoom in, we see that with the grid you follow the main channel with a high resolution, some coarser resolution in the floodplains. You can use a multi-block technology to link different branches together. So this is already focusing all your resolution on the relevant part of the model. There are multiple examples, but 2 examples of hydraulic models like this are Delft3D and Mike 21C by Danish colleagues, but there are several others that use this structured grid mesh approach. So it's much more efficient than a Cartesian mesh, but it requires more work to set up the model and to create a grid. But unfortunately, that's always the drawback. Even a 1D model, it might look simple, but it takes much more time and skill to set it up than a 2D model. And well, a 2D curvilinear model, or we'll use some other models later on, take more time than a Cartesian model, but there is really added value in going in that direction. The structured grid also has some limitations. It only has a limited flexibility in how you can mold and shape the grid. And you see some effects of high resolution grid appearing here in the inner band of a sharp river. And that's because every grid line needs to be continuing in this direction and every grid line needs to continue in that direction. So if I curve it, I get a dense configuration of grid lines over here. So can we do something else? Let's use triangular meshes. So just one step back, we intend to have the Delft3D model also included as a hydraulic model in the DRIHM platform. A 2D version or sister of the Masquerade 1D model is such a model, and I have a picture from one of their standard test cases. You have a triangular mesh, gives you the flexibility to easily create a mesh. However, if you then start zooming in on the main channel, for which I don't have a picture here, but you can imagine that if you have equilateral triangles, something like this, if you try to follow a river and you want to have a pretty good resolution in the lateral direction, you also need the same resolution in the longitudinal direction. So that's limiting the efficiency, and it's also not very nice to have your grid interfaces. If you have a predominant flow in this direction, you would have velocity components pointing in all kinds of directions, where it's a structured grid that follows the channel. You have velocity factors that align with the grid, and that gives also a better numerical solution. So the next step would be to combine the two. That's what we are working on in the Delft 3D system. If we are lucky, we can manage to upload it also to the DRIHM infrastructure. Otherwise, it might be something to be added shortly after the project finishes. But the idea was, well, if we start having a curvilinear mesh for the main channel, we want to be flexible in doing the meshing of the floodplains. And this is maybe an exaggerated case where you have taken a lot of liberty in creating the mesh, but this was the first concepts that we tried to get working. So you can have upstream a 1D channel, and then in your area of interest you can go to 2D and flow back into 1D or something like that. So it gives you maximum flexibility, but you need to decide how to set up your, how to create it. It's not straightforward, just put a rectangular grid over my river. So I'll show you now some examples of grids, not for a river case, but for a delta case, coastal application. This is the Mahakam Delta in the island of Borneo, Indonesia. So we start with a grid covering a whole part of the ocean, and then for that part you can use a Cartesian, more or less Cartesian mesh, and then if you zoom in you go to a curvilinear mesh. We solve fixed things in between transitions with triangles, and then if you zoom in you get meshes that follow the individual channels, some triangles to merge the channels together. Of course there is quite a bit of work in creating such a model, but it's very useful afterwards. It's efficiently doing the simulations. And you can model the very tiny channels as 1D channels in this model. So then the the final one is basically going back. Well, Cartesian meshes, maybe there is a solution. And there are different modeling systems currently looking at this approach and available now. This is some slides I got from my colleagues of the 3DI project, where you try to get but the other models do something similar. You do the hydraulic computations on the discussion, something similar to the fact what you do in a 1D model is you use subgrid information, subgrid cross-sectional area, much higher resolution grid, and use slightly different approaches in what kind of information they use from the subgrid. So it's a fairly new environment, but it allows you to go to extreme detail, and this is an example from 3DI into one of the partners at Delft University, visualizing a very high resolution LiDAR type of imaging, combined with the flooding on the digital elevation model derived from these LiDAR scans. So you can almost go to the square, maybe 10 centimeters, 30 centimeter resolution, but try to keep the computational time of a much coarser model. They do that by solving the equations on the coarse grid, as I mentioned. So it has some drawbacks that you cannot, this grid cell floods, but you don't know which part of it cell floods. So you just take the deepest part and you assume that that part is flooded. But if you have a grid cell that would connect two parts that are separated on the high resolution model, the water will magically move one channel to the other. So you have to work on getting some resolution, sufficient resolution to keep water basins separately. They use a quad-tree grid refinement technology here in the 3DI case, but there are other options as well. I don't want to go into details now, but just to give you an impression of what possibilities there are. So this is a little bit inspired by the previous step where you have set resolution. So let's assume that this is the bathymetry of one grid cell, and you start filling the water. It starts filling, but then suddenly you start seeing water in the second basin, whereas that could not be there in reality unless this barrier has been overtopped. Well, if you don't want that, you need to go to a higher resolution model. So sometimes this is an acceptable step at a certain resolution. Maybe you don't want to have one grid cell for your area, because then it's just like slicing with one water level and filling up the deepest parts. But but if you are looking at the street where the left part of the street is flooded or the right part, that might not be that relevant any more. So the question whether this is relevant is scale dependent. But important way to simplify the model, and that's used by the subgrid models mentioned on the previous slide, and also by the RFSM, rapid flood spreading model, that will be included in the next demonstration. And there they have a smart way of looking at the topography and identifying irregularly shaped subbasins, and use a more simple approach to filling each of them, but still keeping momentum type of dynamics across the grid cells from one to the other. So this is where I conclude the discussion of the hydraulic models in general. It's not so easy to set these models up using a web portal. We have all kinds of user interfaces under development or developed over the years. Something like this, where you have channels, a map with the river channels, cross-sectional areas, bridge locations, all entered in a database, and you can keep track of multiple scenarios, and well, that's bigger developments that cannot that easily be ported to the web. And this is an environment that also can integrate two-dimensional models and look at time series. Just an example of the Cisco area. For the DRIHM project, we are focusing on hydrodynamics, so we focus on the flow only. However, in general, flow is not the only process that you might start looking at. You may start looking at sediment transport, morphodynamics, interaction with waves if you start to go into the coastal areas or in lakes. Water, you start mixing it with data, so you have possibly live data fields, and then in the end you want to go to impact assessment. So this is the bigger picture of where you would like to go with all of these platforms. So you couple all kinds of models together. That's to start to bridge towards the OpenMI. So we will be using OpenMI here. Why? Because our institutes were involved in the development of OpenMI, and it's a very nice coupling standard, but there are several other coupling standards around the world. So this is a little bit like the community-driven standard. There are lots of communities, and we are still struggling to are the core elements in these different coupling platforms. And more these things become alike. And the core elements of OpenMI that I'm going to talk about, you see appearing in other frameworks as well. So what about OpenMI? At the end of the previous century, so 95, 99, people started thinking, okay, we need to do this integrated environmental modeling, coupling all kinds of models together. But some models are developed by Wallingford, some models are developed by DELTARES, some models are developed by yourself, some by other parties. So how can we bring these models and link them together at runtime without changing the code by the various groups just for my model linkage? So you don't want to change the source code when you start the linking process. You want to have changed the source code before that and made it possible in a generic way to couple models together. So the vision was to enable in-memory data exchange between programs which are only brought together at runtime and not thought of coupling before that time. European Commission funded the initial project at the beginning of this century, which led to the development of OpenMI version 1.0, and we started an association, independent association, OpenMI Association, to safeguard the intellectual property of this open standard. OpenMI is an open source standard that different parties can use and include in their model, and then if they implement it, and I'll go and say something about that on my next slide, the models can be coupled at runtime. Then there was a project which ended in 2010 and which delivered us OpenMI version 2. And as you have heard in earlier versions, OpenMI version 2.0 got accepted as an OGC standard earlier this year. And of all the model coupling frameworks, it's the only one that has that kind of that accreditation. So what's needed to make a model convert that into an OpenMI component? The first step is to change your executable into a DLL or shared library. Then the next step is to split the main program loop into an initialize time step, or update as it is called in OpenMI, and finish parts. There are a few more elements to it, but the main ingredients are these. Then a model can be instantiated, it can be started, and then the next step is you query. So you do an initialize of the model, and then there needs to be functions for inputs and outputs. So after initialization, the main OpenMI environment can ask your component what are the quantities that you would like to receive from the environment, and what values can you provide back to the environment. So you need then to provide a list of quantities, units, and spatial locations where you can provide data or need data. So that's sufficient information then for the framework to couple and say, okay, we need this data set to go to this data set from the other component. Quillon showed this morning the slide where the two models are interacting, and so these steps you do before that. You configure which data transfers you want, and then at runtime the system calls get values and set values to transfer data from one component to the other component. And there are all kinds of issues of adapting for different grids and different time stepping, but that's too much detail for this training course at this moment. So I think the final slide is a slide on the Pipistrelle environment. So if you want to use OpenMI, you can most easily use the open source C# environment developed by the colleagues of Wallingford. And in the next demonstration, my colleague will show you how this works and go through some steps with you. I included some hyperlinks, but most likely they will be repeated during the next session. So that's it for me now. Do you have some questions on hydraulic modeling? Yeah?
In the example you showed for Indonesia, I was wondering how is the flexible mesh created in the delta? Is it a manual process, or you have some kind of methodology to it?
Yeah, so the question was how do you create this kind of mesh? Is it manual work, or is it automated, or it's a manual process at this stage. We are looking for different technologies to identify common parts, so that you say, okay, if I have the outlines of channels from a GIS, or can I do image processing to extract the bank lines, but still you want to have a human checking whether that's actually the right thing if you're not smoothing over something that's really important, or so yeah, it's a time-consuming work, but it enables you to run simulations at a scale and resolution that was not previously possible. So the good thing is you can sometimes get students who want to do very nice hydraulic modeling, and they can set up a model, and then you can do follow-up projects using the same model. But so we hope to build portal, not as part of DRIHM, but now I'm speaking on behalf of DELTARES, to be able to share these models, so you can learn and use models developed by others, and the first step would be for this model for San Francisco Bay Area. We hope over the next few months to have that available as an open community model where everybody interested in that area can start working with it. But yeah, it takes a bit of time. but there are logical steps to create, and you start with the channels, and then you start looking at, okay, how can I make these bifurcations, how to grid them. Yes. Yeah, the question is whether it can be coupled to a wave model. Yeah, so, well, this is a little bit look towards the future, but for the structured grid, we have this coupled to this, and basically these four coupled together, and somewhere mid next year for the unstructured, the flexible grid model, all these things will also be coupled together. But I should make the remark that for the DRIHM project and DRIHM infrastructure, we are currently only looking at this one. But there is sufficient opportunity to expand.
Are you going to include data simulation and stream flow observations?
Yeah, this model is already including data assimilation. It can be connected to data assimilation. Actually, if you prepare your model for OpenMI coupling, basically this is a core ingredient of doing data assimilation as well. So you can say, okay, I have a data assimilation framework that can get the model values, the model state, get the data values, and then set an updated state. So there is not really too much of a distinction between model coupling, data assimilation, if you start looking at it at a little bit more generic level. Okay, good. I think that's at least the questions for the moment. I'll be around also tomorrow, so let me